Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
The Heliosphere, our solar system's invisible shield. The heliosphere is a vast, invisible bubble that encompasses the solar system, created by the continuous outpouring of charged particles from the Sun. This immense region, sculpted by the solar wind, forms a protective shield that influences the conditions encountered by all celestial bodies within its domain. At its most fundamental level, the heliosphere is a dynamic and ever-changing structure, born from the interplay between the solar wind, a stream of plasma composed of electrons and protons, and the ambient interstellar medium that pervades the galaxy. The Sun, in its ceaseless activity, ejects these charged particles at high speeds, and as they travel outward, they interact with the sparse material that exists in the space between stars. This interaction gives rise to a complex boundary where the influence of the Sun wanes and the characteristics of the interstellar environment become more pronounced. The journey to understanding this colossal structure has been marked by decades of scientific exploration and technological innovation. Early space missions were primarily concerned with studying the solar wind and its immediate effects on nearby planets. Over time, with the advent of more sophisticated instruments and the launch of pioneering spacecraft, researchers began to unravel the structure of the heliosphere in unprecedented detail. These missions provided the first clues to the true extent of the Sun's reach, revealing that the solar wind extends far beyond the orbit of the outer planets. Observations made by these early explorers laid the groundwork for a modern understanding of how the heliosphere acts as both a conduit and a barrier, modulating the influx of high-energy particles from outside the solar system while simultaneously disseminating solar material into the vastness of interstellar space. At the heart of the heliosphere lies a delicate balance between forces that are as subtle as they are powerful. The solar wind, carrying with it the magnetic field of the Sun, interacts with the interstellar medium in a manner that creates a series of complex regions and boundaries. These regions are governed by the principles of plasma physics, where the behavior of ionized gases under the influence of magnetic fields gives rise to phenomena that are both fascinating and perplexing. The turbulent nature of these interactions leads to a constant reshaping of the heliosphere, where regions of calm and turbulence coexist and evolve over time. This turbulent environment not only influences the propagation of charged particles but also plays a crucial role in determining the overall shape and extent of the heliosphere, making it a subject of intense scientific scrutiny. The protective role of the heliosphere is one of its most intriguing aspects, as it serves as a natural barrier against the barrage of cosmic radiation that permeates the galaxy. By deflecting and modulating the flow of galactic cosmic rays, the heliosphere creates a more hospitable environment within its boundaries, reducing the radiation levels that might otherwise pose a threat to the development of planetary atmospheres and, by extension, to the possibility of life. This cosmic shield is not static. Its effectiveness varies with the cyclic nature of solar activity, which is characterized by periodic changes in the intensity of the solar wind and the Sun's magnetic field. These fluctuations play a significant role in shaping the conditions within the heliosphere, influencing everything from the propagation of charged particles to the temperature and density of the plasma that fills this enormous region. Understanding the heliosphere is not only a matter of mapping its physical boundaries but also of comprehending the intricate processes that occur within it. The interplay between the solar wind and the interstellar medium creates a dynamic laboratory where fundamental physical processes can be observed on a grand scale. Here, phenomena such as magnetic reconnection, where magnetic field lines break and reconnect in new configurations, release energy and drive the turbulence that characterizes this environment. The study of these processes provides invaluable insights into the behavior of plasmas under extreme conditions, advancing our knowledge of both solar physics and the broader field of astrophysics. This intricate dance of energy and matter within the heliosphere is a testament to the complexity of the cosmos, revealing layers of interaction that are as fundamental to the workings of the universe as they are to the survival of our own solar system. The heliosphere also holds a profound significance for the future of space exploration and our understanding of space weather. As humanity ventures further into space, the conditions within this expansive bubble become increasingly relevant, influencing the design of spacecraft, the planning of missions, and the safety of both robotic and crewed expeditions. Variations in the solar wind can have direct implications for the operation of satellites and the integrity of communication systems on Earth, making the study of the heliosphere a critical component of efforts to predict and mitigate the effects of space weather. These practical considerations are intertwined with the scientific quest to comprehend the heliosphere's structure and behavior, underscoring its dual importance as both a subject of academic inquiry and a factor in the ongoing evolution of our technological capabilities. In its totality, the heliosphere represents an ever-changing frontier at the edge of the known solar system, a region where the forces of the Sun meet the vastness of the galaxy. Its study encompasses a wide range of disciplines, from the detailed physics of plasma interactions to the grand-scale dynamics of cosmic structures, and it serves as a bridge between our solar neighborhood and the far reaches of interstellar space. Beyond the inner workings and dynamic energy exchanges within the heliosphere lies a realm defined by distinct boundary regions that have captivated researchers with their complexity and subtle interplay of forces. In the outer reaches, where the solar wind gradually loses its dominance, a series of transitional zones emerge that mark the changing influence of our star. One of these critical zones is the termination shock, where the once supersonic solar wind is forced to decelerate abruptly as it confronts the pressure of the ambient interstellar medium. In this turbulent region, the solar particles slow down and their kinetic energy is converted into heat, giving rise to a complex, energized plasma environment that sets the stage for subsequent layers of the heliospheric structure. Beyond the termination shock, the solar wind enters the heliosheath, an expansive and highly variable region characterized by a chaotic mix of decelerated solar particles and interstellar material. This turbulent zone serves as a bridge between the relatively ordered inner regions and the more uncertain frontier at the outer edge of solar influence. As the flow of particles continues to slow and mingle with the interstellar environment, the heliosphere reaches its ultimate boundary, known as the heliopause. Here, the outward pressure of the solar wind is balanced by the counterpressure of the interstellar medium, creating a dynamic interface where the properties of solar and galactic plasmas converge. This boundary is not a simple, static shell but rather an ever-changing frontier influenced by both the fluctuating output of the Sun and the variable conditions of the interstellar space through which our solar system moves. Observations gathered by pioneering missions have revealed that the heliopause is subject to continual modulation, with its shape and distance from the Sun varying in response to changes in solar activity and the density of interstellar particles and magnetic fields. As the solar system traverses different regions of the galaxy, the characteristics of this boundary can shift, underscoring the intimate relationship between our star and its broader cosmic environment. Integral to understanding these remote regions are the sophisticated measurement techniques and instruments that have been deployed on deep space missions. Probes such as Voyager and specialized explorers like the Interstellar Boundary Explorer have provided invaluable data, capturing subtle variations in particle density, magnetic field strength, and energy distributions far from the familiar environment near the Sun. These instruments detect not only the charged particles that dominate the solar wind but also neutral atoms that, having escaped the confines of solar magnetism, penetrate deep into the heliosphere. When these neutral atoms undergo charge exchange with solar particles, they form energetic neutral atoms that carry information about the conditions at the heliospheric boundary. By analyzing the trajectories and energies of these emissions, scientists are able to construct detailed maps of the termination shock, heliosheath, and heliopause, piecing together a picture of a region where the interplay of forces is both intricate and dynamic. The physical processes occurring at these distant boundaries offer a window into plasma physics under conditions that are impossible to replicate on Earth. The gradual transition from the high-speed, low-density flow of the solar wind to the more compressed and turbulent plasma of the heliosheath reveals fundamental insights into the behavior of ionized gases in weak magnetic fields. In these outer regions, even minor fluctuations in the interstellar medium or shifts in solar output can result in significant changes in the local plasma environment. The interactions between solar and interstellar magnetic fields are particularly important, as they not only shape the structure of the heliospheric boundaries but also influence the propagation of charged particles, contributing to complex phenomena such as particle acceleration and energy redistribution. Such processes are at the heart of ongoing research efforts, as scientists strive to understand the mechanisms that govern the large-scale structure of the heliosphere and its role as an interface between the solar system and the galaxy. The morphology of the heliosphere itself, as inferred from both observational data and theoretical models, suggests a shape that is far from being a simple, symmetrical bubble. Recent studies have proposed that the heliosphere may resemble a comet-like structure, with a rounded, blunt face facing the direction of the interstellar flow and an elongated tail stretching in the opposite direction. This asymmetry is thought to arise from the combined effects of the Sun's motion through the interstellar medium and the directional pressure exerted by the ambient galactic environment. The resulting configuration challenges earlier models and invites a re-examination of how stellar winds interact with the interstellar medium not only in our solar system but around other stars as well. Understanding this morphology has profound implications for astrophysics, as it touches upon the universal processes governing the evolution of stellar environments and their interaction with the broader galaxy. In addition to advancing our knowledge of the physical boundaries of the heliosphere, the study of these outer regions has practical implications for future space exploration. As missions venture further into interstellar space, the ability to predict and navigate the variable conditions at the heliospheric frontier becomes increasingly important. Insights gained from studying the termination shock, heliosheath, and heliopause will inform the design of spacecraft and instruments capable of operating in these extreme environments, ensuring both the safety of future missions and the continued advancement of our exploratory capabilities. The heliosphere, as a dynamic and evolving structure, has implications that extend far beyond its immediate boundaries and into the very fabric of cosmic history and planetary evolution. Over astronomical timescales, this vast region has not only provided a protective cocoon for the solar system but has also recorded the interplay between the Sun and the interstellar environment in ways that are only now coming to light. As the solar system drifts through the galaxy, the heliosphere adapts to variations in the density and magnetic field of the surrounding interstellar medium, undergoing subtle yet profound transformations. These long-term changes, governed by the gradual evolution of the Sun and its motion through a diverse galactic landscape, have likely influenced the flux of high-energy particles that ultimately impact the environments of the planets, including Earth. Understanding these processes offers critical insights into the history of cosmic radiation and its potential effects on planetary atmospheres and the emergence of life. At the same time, the heliosphere stands as a natural laboratory for exploring the fundamental processes that underpin plasma physics and cosmic magnetism. Advanced computer simulations and modeling efforts have begun to unravel how even minor shifts in the interstellar conditions can induce significant changes in the structure and behavior of the heliospheric boundary. These models reveal that the balance between the Sun's outflow and the pressure of the interstellar medium is far from static. Instead, it is characterized by a delicate equilibrium that is continuously adjusted by a myriad of factors including magnetic turbulence, shock waves, and the injection of energy from galactic cosmic rays. This intricate balance not only shapes the way in which the solar system is shielded from harmful cosmic radiation but also provides a crucial point of comparison for studying similar phenomena around other stars, thereby deepening our understanding of stellar evolution and the life cycle of astrophysical plasmas. In addition to its role in cosmic particle modulation, the heliosphere serves as a key element in the broader narrative of space weather and its potential impact on human technology and exploration. As humanity embarks on increasingly ambitious missions to traverse and inhabit the deeper reaches of space, the variable conditions within the heliosphere will play a pivotal role in determining the safety and success of these endeavors. Variations in cosmic radiation, driven by the changing state of the heliosphere, could have significant implications for the design of spacecraft and habitats, as well as for the health of astronauts. The ongoing efforts to model these conditions with greater precision are not only vital for mitigating risks associated with long-duration space travel but also for enhancing our ability to forecast space weather phenomena that can affect satellite communications and power grids on Earth. Furthermore, the heliosphere's influence reaches into the realm of astrobiology, where the modulation of cosmic radiation has profound implications for the habitability of planets. The ever-changing barrier formed by the interplay of solar and interstellar forces affects the rate at which high-energy particles penetrate into the inner solar system, thereby influencing the radiation environment that any emerging biosphere must contend with. This protective function, while not absolute, has likely played a significant role in preserving the delicate balance necessary for life on Earth and may do the same for planets orbiting other stars. The study of these interactions offers a window into the past, providing clues as to how variations in the heliospheric shield may have contributed to periods of climatic change and evolutionary milestones on our planet. Looking ahead, future scientific missions and observational campaigns are poised to deepen our understanding of the heliosphere's multifaceted role. New spacecraft equipped with cutting-edge instruments will venture further into this expansive region, capturing high-resolution data that promise to refine our models of how the heliosphere evolves over time and interacts with its galactic surroundings. These endeavors will not only enhance our knowledge of the current state of the heliosphere but will also shed light on its history and potential future, offering a more comprehensive picture of how our solar system has been sculpted by the forces of the cosmos. In essence, the heliosphere is a dynamic, living entity whose influence pervades every aspect of our solar system's existence. Its continuous evolution, governed by both internal solar processes and external galactic forces, has a profound impact on the conditions that prevail on planetary surfaces and in interplanetary space. As researchers continue to probe its mysteries through increasingly sophisticated observations and models, the heliosphere emerges as a critical nexus between the microphysics of plasma interactions and the macroscopic evolution of celestial bodies. This broader understanding not only enriches our knowledge of the fundamental laws of nature but also lays the groundwork for future explorations that may one day unlock the secrets of the universe as seen through the lens of our own cosmic neighborhood.